部的 pointer。
Okay, yeah. First, I thank the organizer for giving us this chance to talk about our recent work. This work was done with a postdoc of mine, Yoyuki Umeda. Yeah, I think that you must have heard of the QCD because this approach, this non-particle approach, was proposed about 4 decades ago by Schiffman, Bernstein, and Zakharov. And so this has been applied for a long time. And this the QCD rule was based on the elasticity of a physical observable, and is derived from the dispersion relation. So then people have applied the QCD rule to extract the observables from operator power expansion at short distance. So these there are 2 sides of the QCD rules. So one is called the Quark side, another is called Hadron side. So then on the Quark side, people apply the OP, operator product expansion. So and for the Hadron side, okay, for the Hadron side, and we have to know the information from the spectral density. So then people assume the Quark-hadron duality. Okay, then by with this assumption, and then people can extract the non-observables. And then, however, this Quark-hadron duality will apply to the very low energy power, 1 GeV. So then, this is certainly we don't know whether the Quark-hadron duality will hold at such a low energy. So this assumption usually causes large uncertainty. So in this talk, I will propose our alternative method to extract the non-particle observables. Okay, so first, let me define this correlator. This is defined by this current correlator. So this pi is called vacuum correlation, and there are 2 ways to calculate this correlator, a large Q squared. Okay, the first thing for the left hand side, because the Q squared is large, so we can apply the operator product expansion. So we call this Quark side. So you can calculate the diagrams shown here. So the first term can come from the so-called the piece. So this you can go to high orders. So you have 1 from the B order, and then the second order is the alpha of pi. And then you can calculate the higher power contributions. So like the diagram shown here. The diagram shown here is on the
out of battery.
Yes, sir. This diagram shows the contribution from the Boron condensate. So this is a high power contribution. So it's down by 1 Q to force. So this it represents the interaction between the internal quark with the background field from Boron field. And so by applying the OPE, and you can use the perturbation theory to calculate the Wilson coefficient in 1/12 pi. Okay, so you can calculate that it's a higher power contribution term by term. So the people have computed this up to this 1 to the Q6 power. So then this is called Boron condensate. This is called Quark condensate, and this is so-called 4 Quark condensate. And usually people parameterize this 4 Quark condensate in terms of this parameter called kappa. Okay, so the kappa is between the 2 and 4. Okay. So this is so-called factorization assumption. Okay.
What's kappa?
Kappa is just a constant. Just a constant. Because because this is the 4 quark condensate, so you should have a QQ bar squared and then take an average. But now you just parameterize this 4 quark condensate in terms of the diquark condensate. So then you have some mismatch. So this mismatch compensated by kappa. So you can measure this kappa just represent the strength of the quark condensate. Okay, so this is the standard OP particular piece and the higher power contribution. So this is the quark side. Then the second way to calculate okay. Another way to calculate this current correlation is following. So you use the dispersion relation. So, okay, for vector propagation, find the q squared, okay, large q squared. You can write this vector propagation in terms of the this contour integral. So you design a contour in this way, such that okay, then we assume that there's no contribution from large sector. And then this is these two pieces of contours with one below the branch count and another above branch count. So when you go around this branch count, you pick up the imaginary part. So then we can write this vector propagation, okay, in terms of this dispersive integral, and with integration along this positive real axis. So we know again these are easy to understand. You know q squared, we have positive q squared. Then we can have the real intermediate states here. And the real intermediate states, okay, from this vector propagation will contribute this in imaginary part. Okay, then if up to the next order, we know that the piece, okay, given this contribution. So then we just label this particular contribution as A pi. Then I talk about the hadron side. Then for the hadron side, okay, because now we will handle the measured part of the vector propagation. So to pick up this imaginary part, then we insert a complete state into between these two currents. So these are the real state, because we know real state will contribute in the imaginary part. So this is the phase space is behind the moment conservation. So then we isolate the ground state, the first state, okay, into this total contribution. So this is okay, by performing this phase space integration, you can get this data function. So q squared, okay, the photon mass should be equal to the, for example, the raw metal mass. And then FV is the decay constant, which is defined through previous page. Okay. Let's wait for the next.
Computer is even more difficult than QCD.
Yeah.
So what is the Quark-hadron duality?
I still want to find. I don't want to find.
You pay attention.
And there we go.
名字找不到。找不到。
哦，
Imagine this is a defense department meeting. Oh, okay.
Previous page.
这边吗？这个
要回2页。
Okay, then let's come back to this page. Now, so this is the decay constant we want to keep. So this is unknown. Okay, vector decay constant. This decay constant is defined through this mentioned element. So because we insert this complete state, so we have this vector dimension state nothing by this current. And this is the so-called spectral density function, okay, from the continuum, because we have a high states. So the above the ground states, then this above ground state will contribute to this continuum. So it's a continuum parameterized as a spatial density function. And then this is the H that labels the threshold of the continuum. So this SH certainty is smaller than lower than 1 GB squared. So you see that people have assumed that this is a state function. Certainly this is an assumption, okay, not very rigorous, okay. And okay, now what's the Quark-hadron duality? Because we want to calculate the decay constant. So, but we don't know the spatial density by the contribution from the continuum. So how we can do? So that usually people assume that the so-called Quark-hadron duality. So it means that we just assume this spectral density is equal to the perturbative one. Very strong assumption, very strong assumption. So certainly we don't know at which point, above which scale, then this rho h will begin to equal to the perturbative one. So people parameterize this scale, spatial scale is called S0. It's called the duality interval. So people assume that Q squared goes greater than some scale like S0, then the rho h can be almost equal to the perturbative contribution. So this is so-called Quark-hadron duality. So this is the hadron behavior. This is the quark. And we'll just assume above some scale, then they are equal. So this is a very strong assumption, because we know that this S0 cannot be too big. I mean, even though assume or S0 is large enough, this duality should hold. But we know that S0 cannot be too large, because you see, this demonstration will hold when S0 does not exceed the excited state. Because if S0 is larger than the excited state mass, then we have to include two poles. You see here, we just include the single pole. Single pole means that this S0 should below the first excited state. So S0 cannot be too large. So in fact, it turns out that S0 just around 1 GB. So can you believe that the Quark-hadron duality as low as 1 GB? Okay, certainly. So these are major assumptions, and it causes the uncontrollable theoretical uncertainty. But people have used this assumption for 4 decades. Yeah. Okay. Now, so then people equate the hadron side and the Quark side to get the QCD rules. So this is the Quark contribution. You insert the penetration. And you insert the penetration, you have a single pole penetration into the hadron side. Okay, then this data function just give you the first term here, data function. And for this term, okay, then it's an integral, okay, takes the contribution from the above S0 to infinity. Right? And then you look at the right hand side, okay, the Quark side. This is the perturbative piece. It goes from the low. Okay, it goes from the threshold to infinity. So we move the dispersive piece from the left hand side to the right hand side, and you cancel the contribution from the infinity. So then you get the result here. Okay, so you get the result here. So on the right hand side, everything is known if you assume the Quark-hadron duality. So the integration goes from the threshold to S0 because the contribution above S0 has been cancelled from both sides under the Quark-hadron duality. Yeah. So then the right hand side basis is known, so you can calculate. So and then in practical application, people further apply the so-called Fourier transformation, because we know that Quark-hadron duality is now may not be a good assumption. So people apply the Fourier transformation to suppress the uncertain hadron spectral function. And on the right side, the Fourier transformation can also suppress from the higher power, from higher power terms, such that the uncertain contribution from both sides can be expressed. So this for the conventional QC sum rule, the traditional QC sum rule for Russian formation is very crucial. But in my opinion, okay, I will show you that in fact using our approach, okay, this Russian formation is not so crucial. Okay, so and then certainly once you calculate the decay constant using the sum rule, you immediately see that it's very natural that decay constant will depend on Q squared, right? Because you have Q squared dependence. Okay, Q squared is arbitrary. So so then you know that the decay constant will depend on Q squared. We know that the decay constant should not depend on Q squared. So then the people have to assume, okay, demand the stability of the solution. So this requirement fix the choice of S node. So people tune this S node, so-called the duality interval S node. People tune this and then try to get the stability of the solution. You know that because S node, okay, just the state appears very narrow interval. So sometimes the stability does not exist. So then ambiguity will appear. So then the common, you can see that I quoted this common criticism of QC sum rule from this paper. So it means that you have to know the answer first. It means that in fact the predictive power of QC sum rule is not strong. So if you have data, then you can use the QC sum rule to explain data. If there's no data, then you can get whatever you want. Okay, in principle. Okay, then because you rely on the strong assumption like Quark-hadron. Okay, so you have 10% error here, 10% error there. So you are talking about real numbers. Okay, so you can find this comments on this paper. So then our proposal is following. This approach has been applied for 4 decades, and I think we should start to think about how to improve this approach. Okay, first, we do not assume state function because it's not natural. So just for example, if I isolate the ground state contribution into this pole, then the rest, okay, just came as a continuous function. Okay, it's a smooth function in the whole range, so it's not a function. And we do not assume the Quark-hadron at low energy because we don't believe that the Quark-hadron will hold around 1 G. We don't believe that. Okay, but certainly we know that this Quark-hadron should hold. Okay, when the Q square large enough, say few GeV, say 5 G, then this Quark-hadron is reliable. Okay, we know that. So we have to. So we use the Quark-hadron for the high Q square. Then we separate this dispersive integral of this unknown spectral density into 2 pieces: the low energy piece and high energy piece. So lambda is a separate scale. Define the low energy and high energy regions. So we leave the low energy piece on the left hand side. Then this is regarding the unknown because it's one low energy, low energy region. We don't know it. And all the masses, decay constants are also treated on unknowns. Then we move this high energy piece above lambda to infinity, okay, to the right hand side. And the right hand side, there's a term pi Q squared, so the real part, in fact, a large Q squared. And then this piece also contains the information of the vector propagation in a high energy. So for this one, we substitute this particular piece for this spectral density. So on the right hand side is not, we call it as an input. Okay, it's a function of Q squared. Then the left hand side contains unknowns like rho h, decay constant, mass. They are all unknowns. Okay, then we want to solve this inverse problem. Okay, this is so we turn QCD sum rule into an inverse problem. And because we solve it exactly, so we don't need to demand stability because we just get a solution. And what is the inverse problem? Okay, this tell you what's the forward problem. So usually you know the charge distribution at some low s. then you can compute the potential from this charge distribution. So this is so-called formal part. In order charge distribution, you can compute the potential from this charge distribution. And then the inverse problem is that we know the potential, We want to extract the charge distribution, okay, from the low S. So this is this inverse problem is much more difficult than formal problem. Okay. Then we want to treat the spectral density as unknown, right? So then in order to make the numerical analysis simpler, so we expand the spectral density in a series of orthogonal functions. Here we use the Lagrange polynomials. You can use other bases of orthogonal functions. It doesn't matter. The result will not change. So here we keep the only 4 terms. Okay, the up to P3. Okay, you can add more terms. Okay, you can add as many terms as you want. So no problem, because this is a general function. Then we impose the boundary condition, because this means that when S is equal to 0, because the when S is 0, the photon is no mass, the photon cannot decay into real height. So we know that the spectral density should vanish there. And the knowledge one is the y equal to 1. So this condition defines the continuity condition. Okay, we know the spectral density has to be continuous at the separation scale. Okay, because after above the separation scale, we have the conservative expression. So this unknown should be equal to this conservative expression at the separation scale. So this the boundary condition is the continuity condition. So then we tune the other parameters like lambda and v, the mass decay constant and the coefficient of the polynomials to minimize the difference between two sides. So in this way, we solve this inverse problem. And so then kappa, as I said, is wrong. So far we know it's between 2 and 4. So just choose the kappa 2 and test 2, 3, and 4. And this is the standard input, the condensate. For example, you can obtain the condensate from lattice QCD. Then we minimize the difference between the two sides. So this is unknown. The hadron side unknown. This is a known from OPE, the quark side. So we pick up 20 points in Q squared. Then we scan this decay constant mass and the spectral density. We minimize this residual sum of square. So then the minima will give us the best solution. Okay. Then for the Q square, okay, the range chosen as above 10, okay, between 10 and 100. So in this way, we guarantee that the OP, the upper part expansion will hold. So we don't need Gaussian form, because when Q square is large enough, the higher power contribution should be suppressed. So we don't need to apply the Gaussian formation. So we just do it, okay, in the Q space. So then this the result. It turns out that this ground state mass point AGV appears automatically. It's a surprise. Because the lambda, okay, we just scan the RSS on this lambda, the mass plane. So if the lambda is the separation scale, separate the low energy region and high energy region. So it's arbitrary. Then it turns out that this ground state mass is almost independent of lambda. It's about 0.8 GeV. Right at the max of the row 770.
Can you explain the color?
Oh, okay. This deep color is the beta. It's means the beta feature. Yeah, the light color is beta feature.
How do you choose a row picture? The function row.
Oh no, wait. Function row depends on B0, B1, B2. So I didn't show it. So just because it's a multi-dimensional scaling. So I just project the SS minimum onto this plane. Yeah, lambda and V plane. And then use another interesting feature is that you see that the upper branch appears here, right? Upper branch. So what does it mean? It means that we are using the single pole penetration. So it means that this single pole can take mass of ground point A, a ground state mass, but it can also take another higher mass. So this higher mass, in fact, represent the excited states. I'll come to this point later. It represents the excited states. So it means that if you choose the mass as the excited states, you can also fit this OP better. Okay, also, yeah. And yeah. So then you wonder which term on the OP side establish this ground state. Okay, you see the ground state, and we have several terms on the OP side. So which term play a key role? And I show you this plot. So you see, if we just keep only perturbative piece, you can see you don't see the plateau. Don't see plateau. Yeah. And then you add the 1 over Q4 force, the quark and gluon condensed. We don't see plateau either. So it means that the 4 quark condensate plays a crucial role to establish the bound state. Here, we do some fine tuning, so we set the clock equal to 3.2. Now then we come to the decay constant and the decay width. So then again, you can scan the RSS on this lambda FV plane. Again, you see the sum of almost the plateau. So you see that for carbide 2 and 3, 4. And we just looking at the global minima here, we determine the decay constant about 0.22. And then the data is about 0.21. And then using this method, you can determine the decay width too. So you can just replace the pole by this Bragg-Wigner form. Then the decay width can appear. Then apply the same numerical analysis. Then you can see plateau again. Okay, which is about 0.17 GV, and the PDG for the ground state rho is also 0.15. Okay, then come to the excited states. As I just said, the upper bridge of the minimum represent the excited states, but certainly, you see that the excited state is not constant. This is because if you go to the excited states, these excited states become denser in the mass spectrum. So that's why we didn't see a constant. But in order to prove that we really see the excited states, so we use the double pole penetration. We have NV1 and NV2, okay, double pole penetration, and then substitute double pole penetration into the hadron side, and we analyze the RSS again. So you can see that this is the projection onto the NV1 and NV2 plane. You see that this central region with NV1 and equal to NV2 is excluded. So it means that the OPE, okay, the input OPE prefers two-state solution. So the one state is located around 0.75, quite close to 0.78 GeV, the ground state. Another mass here is a 1.3. So it's very close to the first excited state about 1.4. Yeah. So then maybe you are also curious if we should also treat the conventional sum rules as inverse power variable hadron. So in a conventional sum rule, there's no lambda because there's no lambda. Then but there is a scale called S0. S0 is located between the ground state and the first excited state. Okay, so you see, so this you can see that conventional sum rule has very strong assumption, very strict assumption. So you see that within this interval allowed for S0, you don't see plateau. You don't see plateau. So this confirms that you need to know the answer first. So because you see the S0 exists in this range, and then the ground state mass can go from 0.5 to about 1. So suppose we know the raw metal mass around 0.8 located here. then we find that the S0 value of around 1.3, then we can read off the decay constant from S0 equal to 1.3, which is about 1.18. Then we know that the data is about 0.21. Okay. So this shows that if you apply too strong assumption, then you won't get the physical result. So we know that if you go past states by applying the conventional sum rules, you won't get a physical result. It's because when you go to the exact states, the allowed range for S0 will become narrow, because as I said, the exact states become denser and denser. Okay, image spectrum. Okay, so we really test it. So if you insist to use the conventional sum rules, it's difficult to study exact state objects. Okay, so summary. So the conventional sum rules rely on Quark-hadron duality and low energy, okay, which may break and induce uncontrollable uncertainty. So in our approach, we turn the sum rules into an inverse problem. So we solve the non-perturbative examples, like decay constant, mass, decay width, together with the spectral density. Okay, here I didn't show the solution for the spectral density. It's not a state function. It's more like a ramp function. So it will go like this way. So it starts from 0, increase smoothly, and go show a small peak and come down again, and then continue with to the perturbative expression. Yeah. So this is our solution for the spectral density. So obviously it's not a state function. Okay. Then in using our approach, we don't need to apply Borosian information. Sometimes Borosian information is very complicated, and we don't need to analyze the stability because we just solve it exactly. And but it's more surprising that the bound states can appear automatically. So it means that our approach can be used to study the hadron spectroscopy. Okay, Hsiang just mentioned. Okay, so in fact, because of the time limit, I didn't touch the other part of our work. In fact, we applied this new method to study a series of low resonance, really establish all the low metal states, all the known states. We really established one by one. Okay, so from a low 770 to the low 1900, and the mass we obtained are shown here. Basically, they are very close to the values in PDG, and then we also obtained the decay constant shown here. Yeah, thank you very much.
Question from audience. Since you know now the spectral density, are there other applications you can do, and also can check this against this position?
Yeah. Okay. Yes. In fact, if we can push this method further, yeah, I think it can become an analytical non-perturbative approach.
Yes.
Latest QCD is a numerical method, but this one is analytical. So I guess that I think we are very ambitious. In fact,
yeah.
we want to promote this approach in the future, the standard non-perturbative analytical approach.
Yeah. Nice talk. Although I haven't talked about a few minutes, but then I have one question. So in the middle, you mentioned also this Quark-hadron duality. You said that at the low energy, Quark-hadron duality might not work. A high energy, but then if it is, I mean, everything is made of quarks, so to become hadron, it must be some sort of equivalence there. Hopefully, you're going to find the correct form. But then the duality must be there, but then in a different form.
What do you mean different form?
Everything is coming from Quark-hadron. If you assume right.
Yeah. But the duality means that you can assume that the quark result is equal to hadron result.
Yes.
How can you assume this?
Yes, so the everything is the made of quark and the made of gluon.
But you know,
Not because of the quark.
you see, if you calculate some knowledge phenomenon using perturbation theory, you get divergence. So you know
Quark-hadron
that.
duality does not mean you use perturbative theory. Non-perturbative theory should also include it, right? So if you do that, then
But then you're going to find some
you don't
systematic approach to calculate the quark.
Yes. So that's always we haven't found a way of understand how.
This is the way, maybe.
It's true. But then that's also if you look at confirmation, Quark-hadron duality. That's also. Yeah.
Nice comment. Any further question?
Duality, it just mean you can calculate the QCD.
Yeah.
Yeah. You calculate, you go to the same result as the effective field. The meaning of duality.
No. It means that okay, you want to understand the hadron, the hadron behavior, for example. Then you can use the quark language to determine this is so-called quantum duality. But this is not always true. Yeah, because sometimes we know that you would apply the theory, you won't get it right answer.
That means you haven't done correct calculation.
So if you do all the mathematics, you must get you must produce answers.
Right.
So but then calculation may not.
Indeed. Yeah, but so far the method we know is just a perturbative method, unfortunately. So usually people say quantum duality in a strict sense means that we can use perturbative theory to predict the hadron behavior.
No,
but this is not always true. Right. So I think that this, if we can promote this method into to some method to replace the ordinary perturbative theory, it will be great.
So just don't call it hadron, Quark-hadron. It is beyond that, right?
Beyond
Yes. Beyond the perturbative.
Yeah, there's no way we are the same.
Make my point.
Just a minute. Can we use the known spectrum as another input to feed back the system or the spectral density?
Yes, exactly. Yeah. So in fact, okay. For example, the kappa is one of examples because we don't know kappa. It means that we don't know very clearly the full condensed. But in fact, using this mass spectrum, you can fix the kappa. Yeah, this is what you say. Yeah. So use this expanding code to help you to determine some unpopular nodes. Yeah, like a common sense. Yeah.
So can you also see that maybe it's too far, but like that you actually see that you need to have a rise, like an asymptotic series of rising of the spectrum eventually by doing this bottom up. I mean, in the sense of doing like a bottom up bootstrap approach. And you see that the spectrum, eventually you'll see these towers of spectrum.
Yeah, you see this tower.
Yeah, but like it has to go to.
We stop here.
Right.
We stop here. In fact, there are even high states, but we believe we repeat our method, we should be able to get a high state. But we don't see it's a flop because we get each one right. So we try to test this one. We are right. We test it, the high one, we are still right. So then we lose interest. Yeah. I believe it should be fun.
Yeah, I was just asking more about like the emergence of the linear trajectory that you'll see that you must have an
Yes, right. So okay, inspired by your comment. So in my opinion, maybe the QCD vacuum is not so non-trivial. Yeah, because you see, I just used only 3 condensates. I can describe this whole mass spectrum. So it means that maybe QCD vacuum is not trivial as a result.
Great discussion. Thank you. Let's thank Quark-hadron. The title is cosmic radiant scattering at gravitational wave vectors.